Good afternoon, everyone. Welcome to USACM's virtual seminar on uncertainty quantification and probabilistic modeling. My name is Sushanta Ghosh, and it's my pleasure to introduce our speaker, Thomas Swinburne, an assistant professor of mechanical engineering at University of Michigan. He has obtained his MS and PhD degrees in physics from Imperial College and BS in physics from Oxford University. Prior to joining the University of Michigan, he has worked at the French National Research Center, CNRS Physique, the Los Alamos National Lab, and the Oxford University. He has also held invited visiting positions at the University of California, Los Angeles, and the University of Chicago. He has received numerous awards, to mention a few of them: Research Excellence Award from CNRS Physique, Emerging Leader Award for Modeling in Material Science and Engineering from Institute of Physics in both 2021 and 2023. His research interest includes plasticity of metallic alloys, irradiation damage, statistical models, rare event sampling, uncertainty quantification, and forecasting. Please join me in giving a warm welcome to Dr. Thomas Swinburne. The floor is yours.
Okay, thank you, Susanta, for this very nice introduction. So, I will. It's a great pleasure to be here, and I think I'll just get right into it. So, please, any participants in the audience can raise their hand on the chat or ask questions. And if I, for some reason, don't see the raised hand, feel free to turn on your mic and shout at me. Okay. So today I will be talking, as I try to give in this title, work that we've been doing going slightly beyond Bayesian regression and uncertainty quantification for Bayesian regression for the case of misspecified models. And a large part of this work was carried out with my longtime collaborator, Danny Perez in Los Alamos. And I will also talk about some ideas of not just quantifying uncertainty, but also propagating uncertainty through various forms of simulation. And this is work done with another longtime collaborator of mine, Cosmin Marinica from USACM in Paris, and a postdoc of mine, Ivan Maliov, who's now gone to industry. Okay, so I'll try to give sort of a general overview in sort of mainly two expressions that sum up what I'll try to talk about. As I say, the first one, as this is a UQ theme, I'm going to talk about UQ for misspecified models. So that is saying when I have a surrogate model EX of theta, where theta are my parameters, I try to minimize some squared error to some target model. And it's misspecified when I can never exactly match the target data. And then I have, in principle, I would require a parameter distribution. And what is that parameter distribution? And if time allows, I will talk about some work that if we have a parameter distribution, how do we propagate that uncertainty through to quantities of interest for simulation? I will talk mostly about atomic simulation. And in particular, I will talk some work we've been doing at propagating these uncertainties through Monte Carlo or free energy calculations. Okay. So, but I'll mainly focus, as this is in keeping with the theme of the talk, for the misspecified model and the UQ. So as a very quick outline, I will talk very briefly about my domain application area, which is atomic simulation, and try to justify why we might want some uncertainty quantification in that realm and the exact form of uncertainty quantification. And then for this problem, I'll read the main bulk of the talk. We'll be talking about this uncertainty quantification for misspecified models. And that's work that was published just about a year ago now with Danny. And then if time allows, I'll talk about some propagation of this uncertainty through various types of simulation, but we'll see how we are for time. Okay. So as a very, very quick introduction to atomic simulation, just to give a setting here, hopefully these ideas will be more general than just atomic simulation, but hopefully to give some idea. So the general idea is a very common simulation technique where I have a large number of atoms in my system and I effectively apply F equals ma and see what happens. That's broad strokes. That's the idea. So it's the Newtonian dynamics with some model for the energies. This is a long history. If you go back to the simple pair potentials that are still used for glassy systems and are still relevant for example, noble metals. We can think of having a pairwise interaction between the atoms, some form of Leonard-Jones potential or something like this. And then I can look at all the pairs and I can build an energy model for my system. And then the gradient forces provide the forces for Newtonian dynamics, and away we go. Right. This is the general setting of molecular dynamics. Now, in practice, if I have a more complicated system, I want to try to get some chemical accuracy. Normally, this energy is actually for under the Born-Oppenheimer approximation is some quantum mechanical ground state. And even if we try to do some mean field approximation for the electronic contributions, there's still a cubic scaling computation to try to estimate the electronic ground state energy and the resultant Hellman-Feynman forces. So this is prohibitively expensive, and I can only do very, very small systems. So there's a huge and rapidly growing, a long history of producing surrogate models for that electronic ground state energy. This would be really what we're focusing on here, where I'm saying that I have some model form with some parameters that's meant to approximate the quantum mechanical ground state energy. So the input would be my atomic positions, and the output would be an energy and the associated gradient force. And I can think about, at the very simple level, just saying I've got some parameters. What's my mean squared error? I want to try to minimize that mean squared error over some training set. So that's the general setting, and the surrogate model for us is this energy function. So rather than doing a quantum mechanical calculation, I would like to have a surrogate model for the energies. So this is a very generic setting. This has got a long history. This has been there's been a few different prizes around, famous works in this area for a long time. The current, in the current flavor or trend, if you like, is to try to produce very, very large databases covering very, very broad sets of the periodic table. So very, very large databases of quantum mechanical calculations to some level of accuracy. So normally some form of DFT. And we want to try to learn some model. This is what the current thrust is, really trying to learn some model that can cover many, many different systems at once. So we have a general purpose surrogate model. I'm not going to talk any more about these, but we did some work on the MACE model, but there's many different flavors of these types of things around. That's sort of where the industry and academia is more moving to. But even for particular systems, I can really start to build quite accurate energy models. This is much greater than just this pairwise Leonard-Jones type picture. And for most of this talk, what I will really be focusing on is high-dimensional linear models. This is my sort of form of surrogate model. This isn't an essential requirement, but I'll mostly be talking about these linear high-dimensional feature models where I've got my inputs being my coordinates. I've got a vector of parameters, which is somewhere in the dimensionality of, say, 100 to a couple of thousand dimensions, something of that order. And I've got a large number of feature functions or descriptor functions, which are features of the atomic environment. So I could imagine the simplest feature function would simply be the interatomic distances. So these Rij's that I had on the previous slide. But we can have many body interactions looking at capturing the 3, 4-body, 5-body environments around the atoms. Again, I'm not really going to go into much detail here. There is we can think about producing these descriptor functions through a basis expansion of the local atomic environment. So if I produce some set of feature functions, for example, spherical harmonics with some sort of a radial basis, I can expand my local density in this basis, and the descriptor functions are scalar contractions of this local atomic environment. That's a very, very rapid overview. As an analogy, I think a nice analogy is, for example, a Fourier transform, where my equivariant basis, so rather than transforming in a nice way under rotations, I transform in a nice way under shifts in time. I then can expand any signal in this basis set, and the equivalent of these descriptors would be the power spectrum of my Fourier transform. So this is a kind of very, very quick overview of the type of surrogate model that we consider, are mostly high-dimensional linear surrogate models. So this may seem quite simple, but in fact, if you really dig into a lot of these, even these more universal models, you can often profitably frame even these deep message passing neural network models in the language of a high-dimensional feature model. So this type of modeling framework, high dimensional feature models from wavelets to polynomial expansions, Fourier transforms, all sorts of things. This is quite a generic operator, right? So a high dimensional linear model is our modeling framework. Okay. And we can do lots of things with these types of models. So we can simulate, in my particular area, we can simulate things of defects in metals, mechanical properties, plasticity. You can go towards electrochemical reactions. There's a broad range of applications. In all of these cases, we really do care about the accuracy and the error, because the kinetics, especially if we think about diffusion, and definitely if we think about thermodynamics, they can be exponentially sensitive to the energetics of the model via some sort of Boltzmann factor typically. So this is sort of exponential to the beta E, right? And most results we actually care about are typically in some extrapolation in size and in time, by which I mean we are looking at much longer time scales than I can generate with my quantum mechanical oracle, or I'm looking at much larger sizes than I can capture with my quantum mechanical oracle. So this means that our surrogate models must A, be efficient, and also we don't have recourse to an oracle to check if they're wrong in many important cases. So this is really where we want to try to have a good handhold on the errors that these models produce. This is really what we're trying to say. This is the motivation for the UQ, is that in many important settings, I can't just check if I'm right or not. I have to really have some robust bounds on my errors of my model to try to make some trustworthy results. So that's really what we're trying to focus on in our UQ setting. So UQ is a broad topic, and I want to make a quick detail here of the difference between qualifying and quantifying uncertainty, because often we talk about UQ in terms of an active learning setting. We're trying to tell if we're OOD, if we're out of distribution, if we're in extrapolation or not. And I would call that uncertainty qualification. So there's many outlier detection methods to detect whether I should increase the size of my training data, have more atomic environments, and try to improve my model. Right? There's many forms of active learning. So this is sort of one based on the Hanover's distance. There's Max-Vol algorithms. There's various forms of extrapolation grade around. All are leveraging these high dimensional feature functions, these descriptors that I described before. Right? And these are very useful. In fact, there's some very nice work from my collaborator, Danny Perez, but also from other groups, where we can use these measures to automatically generate training data to effectively ensure that most of the time our simulations are in some sense in interpolation in result of these feature functions. This is work that we did recently on dislocations, where we have a potential and we can then check that these large-scale simulations remain within the interpolation limit of our model. However, to be efficient, it's not clear in general, even if we're in interpolation, an efficient model will still have some errors, right? So even if I'm in the interpolation regime with respect to my training data, an efficient model will still be misspecified and will still have some errors. And that's really the error that we're talking about here. We're assuming that under some measure extrapolation, we do not breach that. We're in the interpolation limit, but our model still has error. And that's really the uncertainty that I'm talking about. And I'll come back to that in the next section of the talk. So to really get the idea here is that this is really the topic that we're looking at. We're saying that we want to have uncertainty quantification on the output of our energy model, energies and forces. And we really want to have coverage. What does that mean? I'm sure that in this audience, many people know. We want to have error bars such that the true result lies within the error bars. And this is normally not the case for many UQ schemes. We often underestimate the error. There's an examples provided here, which I'll come back to in a few slides, where we see the ground truth is the black line, the orange dots are the training points, and this is plus minus 3 sigma from Bayesian ridge regression, the blue line with the blue bars there. So you can see that a lot of the time, the ground truth is outside of plus minus 3 sigma, and this would mean that this method does not have coverage for this data. Right? You might say, okay, I know how to get coverage. I can use conformal prediction. This guarantees coverage on my errors, but this has a separate issue in that this only provides pointwise prediction errors. This is saying that I can use CP to try to get some error bars on the output of energies and forces and produce error bars on these. But this isn't actually quite good enough for us, because we don't just want errors on energies and forces, we want to propagate this through the simulation. So this is really another key point that I think is quite generic for computational modeling, is that I have a time step generator, my forces. I can put an error on these, but how do I then get an error all the way out to my results that I care about, right? So in my setting, what does this mean? This means that even if we have an energy model, I might need to evaluate this energy model once per time step per atom. So 1,000,000 atoms for 1,000,000 time steps, I'm evaluating this model 1,000,000,000,000 times to get a result. So if I want to try to express error bars on my result, I need to have a very efficient way of propagating this error through the simulation, accounting for the correlations in that simulation itself. This is why what we really want to have is not just uncertainty on the output of the model, we want to have uncertainty on the parameters of the model. Because if I can assign all my uncertainty to parameters, and then I can work out how my result depends on my parameters, I can then push forward that distribution and produce an error distribution on my results. And that's really what we're interested in. It's not the errors on my individual energies and forces, but the errors on an actual result of my simulation. And if I can do that, another corollary of this is that I can also, if I can work out how my result depends on parameters, I can often confront that result with experimental data or higher level data, and then I can start to look at some inverse problems as well. If I can, separate to the UQ side, if I can express my result as a function of my model parameters, I can start to do some inverse problems. But the main for this talk in the UQ setting, if I want to have coverage, I want to know that my true result is covered by my distribution on results. I really want to be able to produce that distribution of results. I want to have a distribution on parameters. So our main goal here is to find a posterior distribution on parameters that provides coverage over the output of the model. So that's really the setting that we're interested in. Okay, so that's really this is the main bulk of the talk. And this is really what I'll try and focus on, is that how we try to solve this problem, this UQ for misspecified feature models. Okay. So as I said, as I tried to sort of sketch out of that introduction, for both efficiency and also for a number of other concerns, we often want to use some efficient fixed capacity model to run at scale, to run for our simulations. We might be running for large systems for long times. And in our setting, we're going to be mostly focused on these linear feature models, where I've got a set of fixed feature functions and I've got a linear dependence on my parameters. This isn't essential for a lot of the mathematics, but for the algorithm, it turns out to be a bit easier. And as I said, we really want to have uncertainty on my parameters. I want to try when I train on my training data, what after this, can I get a posterior on my parameters? Okay. So this sounds like a classic case of Bayesian regression, right? But this is really what we found when we dug into this, that if you really start to look at this problem from a computational surrogate model, we're actually in quite an odd corner of the Bayesian world. Okay. So the key point really is that our ground truth is deterministic. What does that mean? That means that if I give the same initial conditions, i.e. the same atomic positions to my quantum mechanical code, within a very, very small electronic convergence, I get effectively the same output every time. Right? This is very similar to, for example, rather than looking at these quantum mechanical energies, I could consider integrating an ODE from some initial conditions. If my integration scheme is accurate, then the final conditions after n steps should be the same every single time. I can give you the same initial conditions, I get the same final conditions at each point. So in this setting, we have very, very weak aleatoric error. Right? The underlying ground truth is deterministic. We also, because we're generating these very large data sets, we can have automated outlier detection. Our uncertainty qualification is working well enough that we can effectively ensure that we're in interpolation. We actually have very weak epistemic errors also. Right? I'm quickly in this underparametrized regime where, in a rough rule of thumb, I have many more parameters, I have many more data points than parameters. Right? So n is much, much greater than p. N here is the size of my training set. So I'm in this underparametrized regime. So already the two forms of error or uncertainty that we typically think about in the Bayesian setting, we have strong arguments to believe they're both very, very weak. So this is already showing that potentially my standard Bayesian schemes might not be adequate here. And finally, the most important point, which is often not explicitly talked about in the Bayesian setting, is that any model, almost by definition, my efficient model, my surrogate model, is misspecified, which means that there's no one choice of parameters that can exactly match all of my training data. So this is the same as saying here that over all of my training data, the loss minimizer still has non-zero error. That's what misspecified means in this setting. So it still seems like something you might want to use Bayesian regression for. And I'll try to show you that that's not actually adequate and the solution that we have for this problem. Okay, I'll just have a quick pause. If anybody has any questions, they can please just raise their hand at any moment. I'm trying to monitor that. So, okay, so we're in this setting where we have very weak aleatoric error, very weak epistemic error, and the dominant model error form is from misspecification, which I think in the world of computational surrogate modeling is actually quite common. As I said, we can think about this as looking at a ODE simulation or any form of ground truth where the oracle or the actual target of the simulation has this deterministic relationship between input and output, as we have for quantum mechanical calculations. Okay, so let's just try and show and see how Bayesian regression might fail in this setting. Okay, so this is a test. This is using scikit-learn's Bayesian ridge, right? Where I'm not including the aleatoric error. We're setting this prior to have the aleatoric error extremely weak, and we're fixing that. So I've got a 3-parameter model, which is a constant, a linear, and a quadratic term. And my ground truth is a quadratic plus a sinusoid, right? So in this setting, that's the black line that we're seeing. And the orange dots are samples on this setting. So we can see that this is clearly a misspecified model. There's no one value of parameters that can match the data. And I'm running scikit-learn's Bayesian ridge, looking at the parameter posterior and I'm then taking my parameter posterior. I'm sampling up to plus minus 3 sigma on these parameters. And that's what I'm putting through the output here. I'm taking the range there. That's what the error bars are, the plus minus 3 sigma there from the output of my model. So we can see here, I've got 16 times as many. So I've got 48 data points here, right? So I've got 3 parameters, 48 data points, n over p is 16. And you can see that this is looking fairly sensible, right? I haven't got coverage. This is the issue that I said before. But, I've got some error bars and they're sort of wide. And this is looking, this isn't perfect, but it's looking like something that could be useful. However, if I increase the data counts, so many people might know what's going to happen here, but if I increase my amount of data, I have this pathology where the error bars are getting smaller and smaller, right? So this is, again, if I increase this and I increase this, I can see that my parameter posterior is becoming tighter and tighter. It's concentrating around the min loss value. And this case is really the pathology that we're trying to target here, where even though I'm looking at plus minus 3 sigma for my Bayesian regression, I've got massively poor coverage of my actual data, right? I'm really underestimating the error bars. So you can actually show this analytically. You can apply steepest ascents or Laplace's method to my Bayesian posterior, and you can show that it concentrates to a delta function around the loss minimizer. So in this underparametrized limit, I really have formally no uncertainty on my parameters. And this is a provable feature of Bayesian inference, right? And this is really the issue that we want to try to resolve, is to get away from this concentration to the loss minimizer. So why is this happening on a mathematical level? Why do we have this form, and where does this pathology arise from, right? And this is, again, I say this is a well-known feature of Bayesian regression, but for our purposes, it really is quite problematic because we're in this weak aleatoric noise and weak epistemic uncertainty limit, which is, again, quite common for the computational surrogate modeling. So the thing is that we want to just go back to the Bayesian inference problem, or the Bayesian problem we're trying to look at. Our goal is to learn a model, x of theta, e x theta, that approximates our true model, e of x, right? Now, the kind of setting we might want to look at here, what we would call the predictive distribution, is a functional of my posterior on my parameters. So here, pi of theta is my posterior. I'm going to have a conditional distribution, which is the distribution of outputs given inputs. And I've got a true distribution, which is the distribution of outputs given inputs, this rho E of x. And that's going to be a delta function around the true value. And I've got my model distribution, which is rho E of x and my posterior pi, which is going to be this average over my posterior distribution. So in this deterministic limit that I was talking about, we have this very weak aleatoric error. So what does this mean? This means that my true distribution, so the rho E of x, is simply going to be effectively a delta function. So I can represent this by a very, very thin Gaussian of E of x around the output value. And similarly, crucially, when I run my surrogate model, I am also running it as a deterministic model. So for a given value of the parameters, my output distribution is also this delta function, right? There's this sort of very, very thin Gaussian. And I have this model average distribution, which is directly comparable to my data. So I would want to compare the rho E of x of pi and rho E of x. Those are the two distributions that I would want to compare. And when I have coverage, they should rho of m should match rho of e. Okay. So there is a very simple error metric here. It's the natural metric you might pick, right? So for a given distribution of positions under IID approximations, we can say that what I should try to be targeting is simply the cross entropy or Kullback-Leibler between rho E of x and rho E of x of pi, these two distributions. And you can write this out. You can, up to constants, it looks like what you might expect. Some expectation over the data, log, expectation over parameters on the inside. So this is simply the KL between these two distributions, right? Now, this may not look completely familiar, and it turns out that Bayesian regression doesn't actually target this quantity, right? This error metric. This is for very good reason, and I'll try and describe this in a little bit. This is a work that we found in the process of going down this rabbit hole. Okay, so this Kullback-Leibler divergence, this is what we would call the generalization error, right? This is saying that this is the cross entropy between that model average distribution and the true data distribution. Now, if you look at this, you can see it as an absolutely horrible object to minimize. What this is saying is that for every single data point, I'm performing an integral over all my parameters, the integral over my posterior. I'm taking the logarithm of that integral, the absolute value of that integral, and then I'm averaging over all my data. This is a very expensive and horribly ill-conditioned quantity to try to minimize, and it has no actual guaranteed learning schemes either. So what you typically do, what everybody does, is take a convex upper bound, so-called the Jensen upper bound, which is true for convex functions, such as negative log x is a convex function. So I can swap the order of integration. This is the famous Gibbs-Bogoliubov or Jensen inequality. And I now have instead the expected loss or the negative log likelihood, where now I have a much nicer quantity. I have, for a given value of the parameters, I can average over all my data points. And then I average over the parameters. But in this scheme, it's quite simple to see what distribution is going to minimize this integral. I've got some function of theta averaged over some distribution. So what's the functional minimizer? Simply a delta function around whatever minimizes that function. So that was what we saw in the previous slide on the Bayesian ridge regression, that in the large data limit, my loss is minimized by a delta function, i.e. there are no uncertainties on parameters. And this bound is exactly how Bayesian inference ignores misspecification. This bound is the misspecification difference. Now, there's a further bound we can take, because of course this is for this infinite data limit. There's no idea of epistemic errors here. And there's a very nice work from about 10 years ago where you can connect all this picture to this Pack Bayesian picture to this probably approximately correct Bayesian picture, where we look at this expected loss as in the framework of Hoeffding concentration inequalities, and there I can show that this expected loss is again bounded from above by the empirical loss. So this L hat n is simply the summation over my n data points, and then I have this entropic regularization term, which turns out you can show the functional minimizer there is exactly the posterior from Bayesian inference, where I have a prior and the Gibbs term. So this is exactly what we look at in Bayesian inference. And this, as we showed above, is minimized by this delta function. So this is the kind of hierarchy of terms here. We actually minimize this empirical entropically regularized loss through Bayesian inference. This has an upper bound. There's Hoeffding bounds to the expected loss. But this in turn is only an upper bound to the true generalization error that we care about, this G. And what we saw is that in this misspecified underparametrized limit, this first Hoeffding bound becomes tight. So we can see that my posterior limits to a delta function. And this is really the issue we want to try to resolve here. Okay, so there's an analogy which I'm writing. You can actually go quite far down in this analogy, which I'm writing up at the moment. But if for people from the physics background, you may recognize some of these manipulations through the framework of the Gibbs-Bogoliubov inequality. So we can associate, strictly speaking, the energy divided by temperature as the loss, and the free energy divided by temperature is the generalization error. And just as F is less than U, we have G is less than L. So it's a very, very strict analogy between the two. And you can make a few more connections there, which I'll be writing up soon after I finish some teaching. So this is really the framework we want to have. So what we would really want to minimize is this generalization error, but current schemes are only really targeting the loss. And if you ever target the loss, by definition, you're going to be missing all aspects of misspecification, which, as we've seen, is the dominant form of error. So this is really the crux of of our contribution here. We know that the loss ignores misspecification, and we can write down the generalization error, but it's very, very hard to minimize. It's a very ill-conditioned problem. So we looked at the case that if we take this limit of very, very weak aleatoric error, this deterministic limit, can we derive a condition on the posterior, which any posterior must satisfy to have a finite minima of G? What conditions on the posterior are going to avoid a divergence in my generalization error? So if you take this deterministic limit, you can see that this, as I said before, this conditional distribution becomes a delta function, and it's going to look something like this. So this is, maybe if I can get the, I can't quite annotate here, but so we can see that we have a delta function between the agreement between my model and my truth at a certain value of input and a certain value of parameters. I then integrate this over all parameter space. I take the logarithm of that integral, and then I take an expectation over all of my input data points. So what we want to ensure, to avoid a divergence, we need to ensure that for any value of the input, this integral over parameters is non-zero. That's the main key here, right? So what we need, otherwise we'd have a log zero divergence in my generalization error. So to avoid a divergence in this limit, what we require is that the posterior distribution has mass in what we're calling this pointwise optimal parameter sets, or POPs. So maybe this notation is familiar to you. What we can define as POPs is a set in parameter space defined for each data point. And this is saying that it is the set of all parameters that interpolate the data point. So the POPs for a point X is all parameters such that my model is equal to my truth at X. And in this framework, we can say that misspecification means that the joint intersection of these sets are empty. There is no one parameter that occupies all the POPs over my training set. And that's the definition of misspecification. So another way of saying this is saying that my posterior distribution must have mass in every single one of these sets. Otherwise, I'm not going to get coverage. I'm going to get this divergent generalization error. So we haven't found a posterior distribution, but we have found a condition that the posterior distribution must satisfy. The posterior distribution must have mass in every single POPs, or this pointwise optimal parameter set. And because these POPs are non-overlapping, this forces the posterior distribution to have finite width, even in the infinite data limit, because I cannot satisfy this only if there's some mutual intersection of all the POPs can I have a delta function that satisfies this. So for misspecified problems, I can never solve this through a delta function. Okay. So just to restate that argument, what I'm saying here is that any true minimizer of the generalization error must have mass in all of the in all of these pops, right? So if we want to think about, if you think about the generalization error as an entropy, I want to satisfy this condition whilst minimizing my entropy. Well, to minimize an entropy, I want to be as tightly clustered as possible, right? If I think of maximizing the entropy as just homogeneous, then minimizing the entropy as being as tightly clustered as possible. So if we want to have a variational scheme, we want to satisfy this constraint and try to minimize the support of my distribution. Right. So our ansatz to solve this problem is to find the global loss minimizer, and then we form a set of points which are going to be, for every single data point, I'm going to minimize the loss subject to interpolating that data point. Right. So this is so again, there's nothing about, I haven't invoked linearity at any point here, but this is the time when we invoke linearity in the model. To solve this problem, I can do this extremely efficiently for linear models. I can do this. This is a rank one update. It's an analytic solution to evaluate this parameter in this case. So this is really what we're trying to say here. This is to try to maybe recap that. The pops here in this cartoon, the pops are actually infinitely large sets, but let's just say that they're these blue circles. The red dot there's one dot per circle, and the dot is the loss minimizer subject to remaining in the pops. And I can find these red dots, these are constrained loss minimizers, very efficiently for linear models. So I could do this for nonlinear models, but in principle, I would have to re-minimize. I have to do n minimizations over my data set, which could, we're going down those lines, but you can see how this can become computationally expensive. For linear models, I can analytically update my loss minimizer to produce the interpolating loss minimizer for each data point. So that's extremely fast to do. And then we have all of these data points. I know that I will satisfy my condition provided my posterior covers all of those red dots, all of these loss constrained minimizers. And we played around with a few things. In the end, actually, the simplest and best results we got were simply taking a hypercube that bounds these points. So this is actually very simple to do. You just stack up all of these loss minimizing parameter sets, you perform SVD, one SVD call, and you get the bounding hypercube. So it's extremely efficient, and it guarantees that I have this finite generalization error. So I'm guaranteeing coverage, and I'm guaranteeing this finite generalization error, which Bayesian inference provably does not satisfy for these misspecified problems. So this is an example of the scheme for a very, very simple model where I can visualize my parameter space. So this is fitting a two-parameter model, so a linear model of a constant in a linear term, to my ground truth, which in this case is just simply x squared, right? So what have we got here? I've got, if we look on the left-hand plot, I've got my black curve is x squared. I've got my global loss minimizer is the black dashed line. And here I'm looking at the constrained loss minimizer for x equals 1.1. So I've got my blue circle is the value of 1.1 squared. And the solid blue line is the constrained loss minimizer, i.e. the linear function that minimizes the global loss subject to interpolating the curve at x equals 1.1. On the right-hand side, because this is just a two-parameter space, the pops in this case is a line, right? So this is the blue line on the right-hand side. That is my pops. That's the set of all parameters of this model that guarantee interpolation at x equals 1.1. And the blue dot on the right-hand side is the global loss minimizer in the pops for that constrained to interpolate the x equals 1.1. And now if I interpolate over the whole data set, this is going through my entire data set, that's exactly the same procedure. You can see that the gray line is the set of all of my points. That would be the set of all the red dots on the far left in that cartoon on the far left. And the pops hypercube is simply this pink rectangle that bounds all of my ensemble of members. So this is and what you can see now is that if I now look at the max min over this hypercube on the right-hand side, you can see that my pops is indeed bounding the output of the result, right? So that's really the idea here. Now this is a rather simple example. in this very two-dimensional problem. It's not in one-dimensional input. It's not particularly interesting, but this same procedure can really be applied to much higher dimensional problems. So if we go back to this case that we looked at before with this sinusoidal function and the three-parameter input. So this is this pathology of Bayesian ridge regression, this Bayesian inference that concentrates to a delta. Now, if we go to the POPs hypercube and this scheme that we have, we see that we get this is a real result. We're now getting coverage over this data set. So we really are resolving this pathology of Bayesian regression. We've implemented this in a pip installable code that really follows scikit-learn type syntax. So very much as if you're calling Bayesian ridge from scikit-learn, you can now just call ypred, y-standard, but also now you have ymax and ymin. And this really allows you to produce these max-min bars, which have very strong guarantees on the coverage of the data. And it only takes around a factor of 2 overhead overfitting Bayesian ridge for these problems. So we've done it up to 10,000 dimensional spaces, looking at sort of real problems, and it works. It works efficiently. So this is really please feel free to try out this code and try and break it if you we're very happy to get some feedback on that. And this is really the main result here is that we have this very nice bounding and we have this boundary inputs. So what I'll show, I think, as we're getting close to time here. Okay, so let's give you some examples of how we use this in practice. So this is on a real production model, essentially. This is about a 1500 dimensional linear feature model for a tungsten. This is some sort of test on real problems. So this is quite a high dimensional system. What I've got here is that on a holdout test set. So this is not used for training. We have the black histogram are the true errors, and the green histogram is the predicted error histogram. So this is kind of the weak correspondence between the true errors and the predicted errors. And what we can see is that we're getting very good coverage. The distribution is nicely mapping over, is tight on the actual error distribution. So the green and the black distributions have a good cross entropy between them, a low cross entropy between them. As importantly, what we're really seeing on the right-hand side is the measure of coverage. So this is saying the proportion of these test points that are outside of my max-min bounds. So that's really our strong correspondence effectively here. And so there we can see that as I increase the number of training points, I'm having this rapid decay in the violation of my envelope bounds, i.e. the coverage is increasing rapidly as I increase my training data. So this is really what we want to get. This is really the strong thing that you don't get through many other methods, is that we're getting very good coverage of the data, yet our error distribution is at the level of parameters. So we can really propagate this through simulations very rapidly as well. So this is applying this to the MACE model, one of these big foundation models. This is over the entire materials project training data. And we make no assumptions on the form of the histogram for this model. So you can see this very non-Gaussian asymmetric error distribution of a plus minus 10 sigma over the entire materials project database. And we're matching this really well, right? So this is, again, we're making these very good matches. We're slightly conservative, as you'd hope to be. And again, as we add more data, we're enveloping these very rapidly. So what we're doing here is we're taking the last layer, for people who know about these MACE models, we're taking the last layer of the nodes of the model as our features, and I'm applying a linear model as a corrector to the energy output there. So it's just an extension of the linear part of the MACE readout for people who know these models. But there's many other ways we can linearize and apply this formalism here. As I say, the mathematics doesn't require linearization, but for computational efficiency, we have a linear model. So this is really showing that even on the more complicated and sort of cutting edge of these types of surrogate models, we can really provide very robust uncertainty quantification. And crucially, we have this uncertainty quantification at the level of parameters. So this is something which allows us to propagate through up to actual results that we care about rather than individual forced energy calls. We've done other work this is our work from last year, where also we compare our POPs to the various ensembling, and we can show that there's many issues with ensembling, especially with deep neural networks. And typically people try to make an ensemble and they sort of calibrate it and rescale. So that's the difference between the orange and the green histograms here. So if you just do ensembling, as Bremen would have told you back in the 90s, you're getting way too sharp, way too tight histograms through ensembling. You can sort of rescale it if you like. But then if you then look at the histograms of errors, you can see your calibration is way off. So what we're showing here, this is the, for a given true error, what is the average predicted error? And this is what we're plotting here, right? And so you can see that without any calibration, the POPs through its parameter dependence is really being a very well calibrated error measure. So if I have a broader POPs error bar, this means that the true error is generally expected to be higher. And also we have the case where the minimum of the POPs error is always going to be above that black dashed line, i.e. that we have coverage. So my predicted error bars are always greater than the true error. So these are things that are generally very hard to produce through other schemes. And crucially, unlike conformal prediction, we have this at the level of parameters, so we can propagate through the data very easily. So I think I'll end. I won't talk about the free energy work in the interest of time. I'll just end with one example of propagating through, where we're talking about doing this for minimization, right? So just over the last few minutes saying about, okay, I said we have this at the level of parameters. Can I propagate? I have this now a very good coverage through a parameter distribution on parameters. Can I propagate this through a simulation to results? And in this particular case, I'll be focusing on the setting where my simulation is a geometry minimization, right? So for geometry minimization is a very common, I'm sure most people do this in atomistic modeling, and more generally, it's a form, we find minima in all sorts of simulations, right? And it's a very common in sort of finite element models and all over the place. If I want to try to work out how my solution varies if I change the parameters of my model. So this is a very, this is normally done through adjoint methods in FEM, broad, large history, great scheme of methods for doing this. This would be formally called an implicit derivative. So this is saying that my solution to my minimization problem is defined at a fixed point. So therefore, what is the gradient of that function? And that's going to be an implicit derivative. So this is how my minima structure changes. We actually do this in MD codes. This is a paper with my postdoc Yvonne, again from last year, where we effectively use MD codes as a large parallel Hessian-free solver to evaluate this implicit derivative. And this is actually a very nice way of doing it. It makes it trivially highly scalable. We can do this on 100,000 atom systems for the same, something like, you do for P parameters, you're doing less than P minimizations to calculate very, very small, very fast converging minimizations to work out the various rows of this implicit derivative. And what this allows you to do is allows you to propagate through results that depend on minimization. So this was an example which we did with Danny, where we are taking this tungsten training data, which we're training our model on. This is very, very small disordered cells. I'm producing my distribution on parameters from that small data set. And then I'm testing it in extrapolation. I'm working out things like defect formation energies or surface formation energies, which were not in the training set. And that's the red bars. And then I can use my POPs scheme to produce, and propagating through this energy minimization, to produce max min error bars on these quantities. So what we're seeing here, we're going into more detail in the paper, and I say it's only got a few minutes left. I don't want to abuse your patience here. But effectively, this coverage that we saw on the individual force energy calls, we can propagate through to results, in this case to minimized results. And we again get coverage. This is what you're seeing here, that the dark blue bars are covering the red. Or similarly, if I look at on the right-hand side here, the scatter of the gray points is covering or enveloping the red ground truth here. So we're getting highly reliable points. Now you might say, obviously calculating information energy, these are very simple minimizations and not very expensive to do with a classical potential, but we can also propagate this to more expensive calculations. So we can think about the saddle points, and minima points are also stationary points and are amenable to this treatment of implicit derivatives. So we can also do this for energy barrier calculations. So we're doing the full rescaling of the box and the minimization, and I can then very accurately predict how energy barriers change with the potential parameters. So it allows me to propagate through error bars to energy barriers without having to recalculate anything as well. So there's a lot of ways that we can actually start to not just have UQ on the energy force calls, but really have this on the level of results as well. And we've done this for some inverse problems as well, but I think I'll stop there because we can also do this for free energies, but that's a whole different topic which I won't talk about. So I'll skip to the end slides. That was rather ambitious there, wasn't I, to have all these slides in here? But okay, so with that, thank you very much. I just want to quickly say that this POPs regression, which is you can see on this you can pip install it. You can look at it on my website as well. I've got some information there where we can really produce parameter distributions that have very strong coverage of the output model. And because then we have distributions on parameters, I can propagate these through simulations in a very rapid way. And there's lots of respect for this work, but yeah, happy to take any questions. Thank you.
Thank you. Such an excellent presentation. Let's thank the speaker. And maybe I'll start the question answer session by asking a question myself. Yeah. So,
Yeah.
what happens if the model is really complex? I have like a really deep neural network. Do I have still under representation of the uncertainty?
So sorry, you're saying for the very so at the moment we've been applying this. I mean, in short answer, this would work for any model, right? This would provide coverage for a deep neural network. It's just that in the current implementation, we only apply it to linear models. So, but the scheme is general, right? So it would still produce coverage if we did this for nonlinear models as well. But we're concentrating on applications for the linear case at the moment. In general, when you apply this technique, all of the fine tuning, if you like, is producing error bars that are not too big. You're almost always guaranteed to have conservative error bars. So we're in the opposite problem that you normally have in UQ. Normally, in many schemes, you're trying to avoid having the error bars being too small. Here we have the opposite. A well-chosen posterior distribution has tight error bars, but it will always provide coverage in the large data limit. Is
Yeah,
that?
that's great. That's great. But I have one
Yeah.
tweak in that question, that does large neural network like Bayesian neural network or large stochastic models also fail miserably to reproduce correct uncertainty? Because the
So,
examples you have shown initially are like a cubic feet or so.
oh, I see. So I mean, well, I guess it depends whether it depends whether your error is coming from misspecification or epistemic terms, right? So if I have a very, very complicated model, I may be data limited, right? So for example, if you take a kernel model, like a Gaussian process, there I am never underparametrized in principle, right? I have n equals p, right? The number of data points equals the number of parameters for a kernel model. So I'm always in a data limited regime. So it depends on the form of the model that I'm using. We're concentrating on the case where I have an efficient surrogate model, which almost by definition is in this underparametrized regime where I have quite a simple model form.
Thank you. I think Mike has a question.
Yeah.
Please go ahead.
Thanks, Tom. This is a very interesting presentation, really enlightening. I want to talk a little bit more about that, how you mentioned that these, unlike typical uncertainty estimators, tend to overestimate uncertainty. And I think that's clear in the example that you gave where you're trying to fit the linear model, right?
Yeah.
So if I can maybe make sure I understand this. Essentially, what you're doing is you're putting bounds on the support of the parameter distributions for the type of model that you're assuming to fit, right? So you now have the support, but you don't have the density of that. You don't have any information about density. So when you showed that plot of the parameters that actually fit, really you have that hypercube, but you really just have one line or one curve inside that hypercube that gives the parameters that
Yeah. So
that
it's
fit the pops, right?
yeah,
So
yeah,
you
yeah.
have that you have a in summary, I guess what I'm saying is you have a lot of models in there that are really bad models.
100%. Yeah, this is exactly. It means a fantastic question. It's exactly where we are with this. I mean, so I I think I'll make this kind of two points. The pops in this example is the blue line on the right hand side. That there's a infinite number of models that will interpolate that data point.
Hmm.
And then if you think of the ensemble of all of these sets,
Right.
one per data point, all I require, all I know, all our analysis has shown is that the true posterior has to have mass in each one of these sets,
Hmm.
right? So that's the condition. And then one way of satisfying that, at the same time, of course, as I'm sure you see, if I just naively, for example, looked at the ensemble of all these sets, it would be madness, right? I'd have just, infinitely bad models. So what we try to do now is try to minimize entropy while satisfying that mass occupation condition. And our ansatz for doing that is finding the loss minimizer in the pops, so that's the blue line, and then restricting, having a model that has compact support and covers all of these points. So that's sort of that's kind of two steps in of satisfying this condition. The formal condition is that any um, any distribution must have mass in every single pops. But the next stage of doing this hypercube around the points, you're completely right that we would actually want to have, there's many more ideas that we could try out for ansatz here. But we did try a few, and we looked at sort of, try to do some ensemble reweighting and various things like this. But we actually did not find better results than just the simple uniform hypercube so far. But I think there's lots of different directions to try to improve the ansatz effectively there. Yeah.
Yeah. Thank you.
Okay. Thank you. So maybe Ruda has a question. Can you please go ahead?
Yeah. So also on this pops, I'm just curious. Maybe I lost it, but how do you compute the pops?
Yeah, so the pops, we don't actually, in this case, we can analytically show what the pops is. The pops is this set, which is the blue line on the right-hand side. So that's the set of all parameters that that interpolate a given data point. So for a linear model, this is going to be a hyperplane in my parameter space. Then what we actually do for the loss minimizer of the pops is this constrained minimization condition. So it is, here we are, this line here. So this is minimizing my loss subject to interpolating that data point. And that's the red dot here. So the pops is an abstract definition. The pops is the set of all parameters that interpolate a given data point. That's the pops for that data point. And then I find the global loss minimizer in that set of parameters, if that answers your question. So on this very simple example here, the
I,
pops is the blue line on the right-hand side, and then the loss minimizer in that pops is the blue dot on the right-hand side.
and so you would loop through all your data points?
Exactly, yeah. So this is the main reason why we're applying this to linear models, because we can do that operation analytically for the linear model. So if you just have a Lagrange multiplier for the interpolation, you can do it by hand, and you can show that you can relate. It's just one inner product gives you one matrix vector product gives you the updated interpolating solution from the loss minimizer. So we don't actually do n minimizations because we can do this analytically for linear models. So for nonlinear models, we're investigating various directions to make this efficient for non-linear models. But informally, you would want to be doing a minimization per data point, but we don't actually do that in practice.
Yeah, I see.
Any other questions? If there is no other question, in the interest of time, we would like to thank our speaker once again.